All right, so now I will introduce some few more concepts, which are the closure, interior, boundary of a set, and the associated notion of a cover of a set. Okay, so now I'm talking about a general set. I'm not restricting myself to open sets. Neither am I restricting myself to closed sets. A general subset of topological space. So how do you define closure of a subset A of X? See, this A is neither open nor closed. I'm not putting, it could be open, closed, or anything. So general subset, okay? The closure is defined to be the smallest closed set that contains A. Let me draw a diagram. So this is X, and then I have an arbitrary subset, which is A. Now, you consider a closed set, C, which contains A. But this has to be the smallest closed set which contains it. All right. So the way, how do you find out smaller? Because we don't necessarily have the definition of a distance to determine large or small. Well, the way you define smallest is you list all the closed sets C which contain A, C sub alpha, all the C sub alphas which contain A, and you take the intersection of all of them. And whatever will be left over, because arbitrary intersection of closed sets is also closed, whatever will be left over is defined to be the smallest. That is why smallest is quote unquote closed set, which contains A. All right, so this is defined to be the closure. The smallest closed set, which contains A, is called the closure of the set. Second property is known as the interior of a set, interior of a subset, I'm sorry. So the idea is that this has to be the largest open set which is contained inside A. So let me again draw a diagram. So this is X. And then again we have some subset A, not necessarily open or closed. And then let me redraw this. It's a bit larger, so that will help. So this is A, which is a subset of X, and we can find the largest open set which is contained inside A. Okay, this largest open set which is contained inside A is called the interior. Again, largest within quotes. The reason is that there's no notion of a distance, so large and small we cannot define as such. The way we define largest is that I list all the open sets which are contained inside A, all of them, and the union of all of them will be, because arbitrary unions of open sets is also open. So the union of all the open sets which are contained inside A is the largest open set which is contained inside A. So that gives you the interior. So let's say this is the union of all the open sets which are contained inside A. So that shaded region will give you the interior of A. So we have the closure of A, smallest closed set which contains A, and interior, which is the largest open set contained inside A. Okay, and then as you can imagine, the difference between these two is called the boundary of A. So the boundary of A is given by the difference of the closure of A with the interior of A. Okay, as a homework exercise, you should prove that that the boundary of A, which is given by this symbol curly D, okay, D of A. So closure is denoted by the symbol CL of A. Interior is I of A, and the boundary is given by curly delta of A. Okay, this derivative of A or something. So as a homework, I'll ask you to prove that this boundary of a set is always closed. Okay, please do that. It takes a few minutes to prove this. All you have to show, as most of you know, to prove something is closed, all you have to do is to show that the complement is actually open. Complement is contained in the topology T. It takes a couple of minutes to show this, but I would invite you to do this. And now for the important concept of a cover. Now the idea is, again, let me draw a diagram. That's very important. The idea is, let's say you have some set A, and the cover of the set A is the collection of open sets whose union contains A. So you have a collection of open sets, O sub alpha. Alpha is an index which numbers those open sets. Now all of these overlap with A, and the union of all of these contains A. So union of all of these contains A. Then we will declare this collection of open sets, O sub alpha, to be a cover of it. We say that this collection of open sets covers it. Okay? There's no other restriction on them. As long as you find a bunch of open sets, the union of which contains A, then we will say that the set of this open sets collection is a cover of A. Okay? Some people are a bit pedantic, and they might say, well, this is an open cover. Every time I mention the word cover, I will always mean the open cover. Okay. All right. So we have learned about the cover. Let me go to the next slide, which is some properties of topological spaces, which are compactness and Hausdorff property. So let me just. So how do you define a compact set? Okay. A set A, which is a subset of X, is compact if every open cover, so emphasis on every open cover of A admits the finite subcover. So you have this collection O sub alpha, where alpha takes values, let's say, from 1 to infinity, for example, infinite number of them. The idea is that a finite sub-collection of these also will cover A. Okay. So if it happens for every open cover you can imagine for A, then we say A is compact. It's a very strict property. Every open cover you can write down for A must admit a finite subcollection or subcover. Okay. Again, I will give some examples to substantiate this. Let's consider topology on the real line and this open interval, which is an open set, open interval A comma B. We can show that this is non-compact very easily. How? We just specify a cover which does not admit finite subcover. So actually this is a counter example because this is non-compact. For example, this is the cover O sub n, where n goes from 1 to infinity. This is an infinite collection of open sets which cover this, so you can easily check. So the idea is A, these are open intervals, B minus 1 over n. Okay, so it won't reach B unless you take n equals infinity. Okay, so you have to take union of all of them all the way up to infinity, n equals infinity, in order to cover A comma B. If you stop at some finite value of n, then there'll be a gap left between B minus 1n and B, because this is a positive number. So it will not reach all the way to B. So this cover does not admit a finite subcover. Hence, if we find one exception, that is, the job is done, because compactness said that every open cover should admit a finite subcover, and we are able to find a open cover which does not admit a finite subcover. So that immediately proves that A comma B is non-compact. Now, the idea of compactness might be very difficult to grasp when exposed to this concept for the first time. And usually people develop an understanding of it over time. But as a heuristic way of thinking, I will say that you should think about compact sets as something which has finite volume and includes the boundary points. Okay, some set if it has some finite area or finite volume, and if the boundary points are included, then we can think of it as a compact set. So this is extremely heuristic, and many mathematicians would take umbrage at the way I'm motivating this. But I think it is very important to have some fuzzy idea of what this physically means. So if this is all abstract, think about a compact set as something which has finite volume and boundary points are included. Okay. And as a homework, I'll ask you guys to show that the half closed, half open interval A comma B or the full real line, the entire real line itself, are both non-compact, but the closed interval a comma b is compact. Okay, for finite a comma b. If a and b are finite, then you can show this is compact. Okay, so again, as you can see, a comma b are finite, then this will have a finite length. On the other hand, because it's a closed interval, boundary points are included. So you can get an idea of why I said that you can heuristically think of compact set as something which has finite volume and boundary points included. This is related to this general theorem, is that every closed and bounded set in Rn is compact. Okay, every closed and bounded set in Rn is compact. Now, closed, everybody knows what a closed set is in Rn. Rn, with the standard topology, open balls give you a basis for the open set, basis for the topology. And if you take the complements of those become closed set. Now, I haven't introduced what is a bounded set, but the idea is that if you can accommodate any set in Rn inside a ball of finite radius, inside a finite ball, then I would call this set to be bounded. Okay, so every closed and bounded set in Rn is compact. Okay, so this is exactly what I'm was trying to make you guys think about. Think of it as something with a finite volume and includes boundary point. All right, so a corollary of this general theorem is that S2 is compact in R3. So this two-dimensional sphere, two-sphere, is actually compact. R3 is non-compact, we have seen before, but S2 is compact. And the very easy way to see this is simple. S2 is actually the boundary of this sphere, of this ball. S2 is the surface boundary. And boundary of a set, as we know, is always closed. We proved that, I suggested that in the last slide and left it as a homework. So because S2 can be realized as the boundary of a set, hence it must be closed. So it's closed, and because it can be fitted inside a ball of finite radius, it is also bounded. So it's closed and bounded, hence S2 is compact. I hope this notion is clear. People need to think about this a couple of times to get a hang of this. Please do that. Next notion is that of a Hausdorff space. This is a property of topological spaces, Hausdorff separable property. The idea is that, let me just draw it. Let's say this is a topological space, X, and let's contain 2 points, P and Q. Little p and little q. So the idea is I will call X to be a Hausdorff space if, no matter how close P and Q are, I can always draw disjoint neighborhoods, disjoint open neighborhoods. See, these two open neighborhoods do not come into contact, do not overlap. So we can, for any pair of points, no matter how close, I can always draw two neighborhoods which are non-overlapping or non-touching. Then the space becomes separable. Each pair of points can be separated into two different neighborhoods. As when we were students, I remember some people joking about it. Hausdorff can be thought of as Hausdorff, two people who are Hausdorff in different houses, Hausdorff property. So no matter how small neighborhood, but we can always find two neighborhoods which are non-overlapping for two distinct points. Okay. Although it's a bit pedantic, but actually, it's kind of important. And you see, almost all physical space examples I know are Hausdorff. But Hawking and Ellis, page 13 to 14, you can find a very funny counterexample. And the counterexample will demonstrate how contrived that example is. That you have to really work hard to construct a space which is not Hausdorff. So most of the time, I will take it for granted that all of the spacetimes I will consider in derivativity are Hausdorff. Okay. All right, now we come to a very important notion, which is that of a continuous map between two topological spaces. As I've mentioned in the intro, that this generalizes the notion of continuous function from R to R, the continuous function of a single variable. This is generalized. Let me just state the definition. So a map between two topological spaces X and Y, script T and script S are the respective topologies. And F is a map which takes you from X to Y. So let me just draw. You have X, and you have X and Y. And F is something which takes you from X to Y. Okay. Now this is the map between sets. What is we can ask what is the new feature here? So first thing is that X and Y are not just random sets. They're actually sets which have a topology, so they are topological spaces. And F is continuous if the pre-image, so let's take an open set in Y V. The pre-image of this, that is a set of points which from which the set of points in X which are mapped to points inside this V, that is also an open set. Okay, so the pre-image of this open set is an open set. Note the difference. I didn't say that an open set is mapped to an open set. All I'm saying is that that is not the way you can define a continuous function. The idea is that you take open set in Y, its pre-image, which is what I'm defining F inverse, pre-image is actually an open set. Okay, that is, if that criteria is satisfied, then we will call F to be a continuous map. At the first side, you might say there is nothing to do with continuous function, which if a continuous function is given by a function whose graph is given by a continuous curve, there is no resemblance with that picture because this is too abstract. All I'm saying is that if pre-image of an open set is an open, pre-image of open set is open, then the map is continuous. So how do these ideas actually gel? How do I know that they are the same thing? Well, let me just demonstrate using an example. So the familiar example setting is, of course, single variable calculus, in which we have a map from R to R. So this is F is a function, and the graph of the function is expressed as Y equals Fx. We are plotting Y. So in this case, X to Y, X is also R, and Y is also R. Topological space X and Y we had before. This big X is also R, and Y is also R. Okay, so Y. And then, sorry about that. And the horizontal axis, of course, plots points of X. Now you can see this is a continuous function which you're familiar with. The graph of the function is a continuous curve. Now let's take an open interval on that, on the Y. So V, this is the open set V here, which is given by this closed interval CD. And we can ask what is the pre-image of this point. So we can see that would be, so C and D on the curve, that when you land on the x-axis, you get this open interval AB and A prime B prime on the left side. So CD, you can have the value of CD when you are in this open interval A prime B prime or A and B. So F inverse of this open pre-image of this open set on Y is actually union of two open intervals, and we know because open intervals are open sets, their arbitrary unions are also open sets. So the pre-image of an open set is an open set. So that's why this is a continuous function. This is a continuous map, which coincides with the definition of a continuous function. On the other hand, let's look at the other example in which the graph of a function has a break in it. As you can see, the graph of the function has a break in this region. And let's see what happens when we try to obtain a pre-image of an open set in Y. So again, consider this CD interval, open interval in Y, and part of this falls in the break region. What is the pre-image? So on the left, we can trace it back to anything in this interval a prime b prime inside this. So one side is of course the open interval. On the other hand, in the break side, in the side that is on the positive x-axis, where the break is appearing, what we can see immediately is that C comma D is mapped to a half open, half closed, because no points beyond this point B are going to have an image. So image in Y, so this has to be excluded. So in this case, C comma D, its pre-image in the X on the right axis is half open A comma B, half closed on the B side. Okay, but this is a half open, half closed interval doesn't qualify to be an open set under the standard topology. So its union, the union of these two will also not be an open set. So the inverse or the image, pre-image of an open set is not open. So whenever there is a break, we can see every time that the pre-image of an open set which falls inside that break region will not have a pre-image which is open. Okay, so this sort of establishes the equivalence between the usual notion of continuity as a break-free curve with the notion of the topological notion of a continuous map in which the pre-image of every open set must be open. All right, now that we have defined continuous maps, this is our last slide, which is regarding homeomorphisms. These are very special categories of continuous map. So these model the notion of a continuous deformation of an object into another object without tearing or gluing, without ripping or gluing it. Okay, whenever we have such ripping or gluing, that doesn't qualify as a continuous deformation. That's why topology we refer to as Play-Doh geometry. You've seen children in elementary school play with Play-Doh. A lump of Play-Doh, they deform into one shape to another. For example, you can triangle, you can deform it into a rectangle without ripping or gluing, or a circle, or some random shape, which is like this. So these are all continuous deformations of each other. Okay, continuous deformations meaning deformations without ripping or gluing back. Okay, so homeomorphisms capture this aspect of continuous deformation. And the example I'll just highlight Nakahara's book. The coffee cup can be continuously deformed into the donut. Okay, so the coffee cup and the donuts are continuous deformations of each other. Similarly, and this is easy to see, I can of course shrink this dimension of the coffee cup, and then the handle with this is left over looks like a donut, almost like a donut. All right. On the other hand, so if I shrink this dimension all the way, so then this coffee cup gets an appearance which is like this. Shrink in this direction as well, and then it can be easily deformed to a donut. So these are continuous deformations of each other. And a slightly less non-trivial example, which is there in Nakahara, I like this a lot, is that a pair of dealing circles, that is two circles are there which are not linked, and a pair of linked circles, they are continuously deformable. And this might appear very counterintuitive, but if you think a little bit, there's a clever way you can see that they can be deformed into each other. You might think something which is a linked circle versus something which is dealing, how is it possible that they are continuously deformable? But they are. You just have to imagine yourself in four-dimensional Euclidean space. If you imagine yourself in four-dimensional Euclidean space, this becomes very obvious. Of course, no one can imagine a four-dimensional space, but the idea is that there is an extra dimension in which you can move around, and you can de-link the two circles into two de-link circles. All right. If you can embed these rings into R4, it becomes obvious. All right, so homeomorphisms capture this notion of smoothly continuously deforming from one shape to the other. That's why topology is called Play-Doh geometry. So let me give the formal definition. A continuous map from a topological space X to another topological space Y is called a homeomorphism if two criteria are satisfied. One, that the inverse map exists, the inverse map is not guaranteed to exist. So we have to assume that the inverse map exists so that we can go back and forth. And second, not only f is continuous, but f inverse, the inverse map is also continuous. If you have this notion, so bijection as well as continuity of the inverse, both of the assumptions have to be, both criteria have to be included. Then we say f is a homeomorphism between x and y. So x and y, if there exists a homeomorphism in x and y, we call x and y to be homomorphic to each other. And homeomorphism is between two spaces, which is a kind of topological equivalence. That means we can continuously deform one to the other. And from the point of view of topology, we don't distinguish between those two objects because one can be continuously deformed into each other. Okay? Then in some sense, they are equivalent. So this equivalence is denoted by this. Topological equivalence is given by this congruent sign. So x congruent to y actually means x is homomorphic to y. Okay, homeomorphism is a very key idea, right? And a related idea to homomorphism is that of topological invariant. So most of you are students of physics, and I don't have to motivate why invariants are important quantities. For example, in special relativity, you've learned about the Minkowski space-time interval, which is a Lorentz invariant. So invariants play a major role in physics. And in topology also you can have invariants, which are objects or quantities which are left invariant under homomorphism. And those quantities which are preserved under homomorphism are called topological invariants. And some examples are properties such as compactness. You know, a compact space and a non-compact space, they can never be homomorphic. You cannot continuously deform a compact space into a non-compact space. Okay, this is not going to be possible. So compactness is an example of a topological invariant property. Connectedness is also another invariant, topological invariant. You cannot take a disconnected space and then somehow smoothly deform into a connected space because going from disconnected to a connected space, you need to glue. You need to put them together, join them. So gluing is not a continuous deformation, so it's not a homomorphism. So a disconnected space can never be topologically equivalent to a connected space. So connectedness is a topological invariant because it remains preserved under homomorphism. Similarly, Hausdorff property is also a topological invariant. We can never convert a Hausdorff space into a non-Hausdorff space, a separable space into a space which is not separable. Okay, so these three properties are topological invariants. There exist many others. I'm not going to list all of them, but these are three prominent examples of compactness, connectedness, and Hausdorff property. These three properties are topological invariants. One prominent counterexample is boundedness, and I will give one example in which it will become obvious. For example, the open interval a comma b, where a and b are finite, this open interval will be homomorphic to the full real line. And we know full real line is not bounded, it's unbounded. So the finite open interval which was bounded can be mapped, continuously mapped, not continuously, it is homomorphic to the real line. So boundedness is clearly violated by homomorphism. So boundedness is not a topological invariant. So now let me give some examples which will make the case stronger. First thing I wanted to prove or show is that the finite open interval a comma b is homomorphic to the full real line. Okay, how do you see that? Well, I write down a map which is f of x. So x is any point in that open interval a comma b, and f of x takes you to the full real line. You can check this function is something like this. So you can check this is if you plot the graph of this function, this will be a continuous function. If you take the inverse of this is an invertible function. I just need to take tan of both sides, and that function will also be a continuous curve. It will have a continuous curve. So at least in the real line, so the right inside this function is continuous in a comma b. Its graph of this will be continuous. On the other hand, when you take the inverse, you can show that function tan of fx is a continuous function. So as you can see, under this map, the point A is mapped to minus infinity. So A, if you plug in this function, you get minus infinity, and if you plug in B, you get plus infinity. Okay, so this A comma B finite open interval is mapped, is homomorphic to the full real line. Also, heuristically, you can think about taking an open interval and you're stretching the ends of it all the way to minus infinity. So this is a continuous deformation because there is no tearing or gluing involved. So heuristically, also this makes sense. Every open interval, I can stretch it indefinitely, and it will be converted into the real line. What are counter examples? Counter example, as I said, the closed interval minus 1 comma 1 is not going to be homomorphic to the open interval minus 1 comma 1. The reason is that here the boundary points are included, and if you want to convert one to the other, you have to either add the boundary points. If you want to convert the open interval into the closed interval, you have to add the finite boundary points. And if you go in the reverse direction, you have to rip or tear out or remove the boundary points. So no kind of gluing and tearing is allowed. So heuristically, it is obvious. But to write down a continuous map, write down a discontinuous map is, of course, the direct way. We will not do that because, as I said, most of the time we will skip elaborate proofs for simple heuristic argument based on geometric intuition or physical intuition. Similarly, you can show that the circle R1 is not going to be homomorphic to the real line. The answer is very easy. You can think of the real line as extended. In order to convert the real line into a circle, we have to join minus infinity, infinity together to form a circle, and that is not allowed because in continuous deformations we don't allow joining, gluing, or tearing apart. Okay. Similarly, you can show that the circle is also not homomorphic to the closed interval minus 1 comma 1 because again we need some gluing. All right. So I hope the idea of topological invariant is obvious, at least heuristically. As I said, that this is not a course on topology, and we just need to appreciate the underlying notion. That's all. Our aim is very humble. We don't want to be experts in topology, but rather understand some of the underlying notions. All right. So I think that will conclude the lecture today. And here's just a simple summary slide. What we did today, we introduced the concept of a topological space. We introduced the notion of open sets, which allowed us to define a topological space. And we gave some prominent examples which are useful. For example, the usual topology in R and Rn, and then use topology on spheres. Then we introduced the notions of a neighborhood, of closed sets, connectedness. We introduced the notion of an open cover and compactness. And the notion of a cover allowed us to define something which is compact. And we also learned about the Hausdorff problem. At the end, we introduced the notion of a continuous map between topological spaces, which is an abstraction of the notion of a continuous function of a single variable. And this is done, again, accomplished using open sets. Open sets are a key notion. And finally, we introduced the concept of a continuous deformation or homeomorphism and the idea of a topological invariant. Okay, so we will stop here and we will we'll pick up in the next lecture. Thank you.